Good morning friends. After the discussion of the nuclear fission process and also about the nuclear reactor, now we are going to discuss about the nuclear fusion process. Already we defined the both processes, the fission and fusion process. In fusion process, the light nuclei combine to form the heavy nuclei, and the energy is also released during this process. This process is known as nuclear fusion process. Actually, this topic of nuclear fusion is cancelled for your board exam, but for your information and also for competitive exam, we are considered here. That is not asked in board exam, keep in mind that. So here, the topic is that the question, what is the nuclear fusion? Explain the process of the thermonuclear fusion as a source of energy in the sun and the star. First, what is the definition of nuclear fusion? When the two light nuclei fuse to form the heavy nucleus, energy is released. This phenomena is known as nuclear fusion process. Again, when the two light nuclei fuse to form a heavy nucleus, energy is released. This phenomena is known as nuclear fusion. Right? Okay. We know that the sun and the star radiate the energy since the thousands of years. Right? So which process takes place inside the sun and the star? So as a result, this much amount of the energy is released continuously since the thousands of years. Here we are going to discuss this thing. The thermonuclear fusion is the source of energy in the sun and the star. So we believe that the thermonuclear fusion process takes place inside the sun and the star. The interior of the sun has the temperature of 1.5 to 10⁷ Kelvin, which is less than the estimate temperature required for the fusion of particles of average energy. So how the thermonuclear fusion process takes place? So here the important thing is that the temperature is required, the required temperature. Interior of the sun has the temperature is 1.5 to 10⁷ Kelvin. This value of temperature is less than the estimated temperature required for the fusion of the particle of average energy. Inside the sun, whatever the temperature is 1.5 to 10⁷ Kelvin. That is the less temperature compared to the average required temperature for fusion of the particle of average energy. Now, fusion in the sun involves the proton whose energy are much above the average energy. In the sun, whatever the fusion process takes place, this fusion process involves the proton of the sun. The average energy of this proton is much more than this average energy of the particle. The fusion reaction in the sun is a multi-step process. Whatever the fusion process takes place in the sun is not occurs in the one reaction. That is take place in multi-step process. The fusion reaction is occurred through the following two steps. So we believe that whatever the thermonuclear fusion process takes place inside the sun or the star is two kinds, either the proton cycle or the carbon-nitrogen cycle. One is the proton cycle and second is the carbon-nitrogen cycle. Again, the fusion reaction occurs through the following two steps. One is the proton cycle, second carbon-nitrogen, that is denoted as CN cycle. That is denoted as CN cycle. Okay. The fuel in the sun is hydrogen, that means the proton in its core, and hydrogen burned into helium. In the core, that means the central region of the sun, the hydrogen is placed. This hydrogen is burned and converted into the helium during the fusion process. The proton-proton cycle is represented by the following reaction. Here we discuss about only the proton-proton cycle takes place inside the sun as a thermonuclear fusion process. So, proton-proton cycle is represented by the following reaction. So, first reaction is that hydrogen combined with the hydrogen, that means the proton is combined with the proton. The deuterium and positron plus neutrino plus 0.42 MeV energy is released. Here the hydrogen or the proton are the light nuclei combined to form the deuterium plus positron plus neutrino plus 0.42 MeV energy is released. So in which the two hydrogen combine to form the deuterium, positron and the neutrino with release of 0.42 MeV of energy. Okay. This positron react with the electron and two gamma radiation plus 1.02 MeV energy is also released. Again, the positron and electron combine to produce the two gamma radiation with the 1.02 MeV of energy. So whatever the positron is obtained by combining of the two hydrogen, this positron combined with the electron to produce the two gamma rays or the two gamma radiation with the energy 1.02 MeV. And this deuterium 1H2 again combined with the hydrogen, that means the proton, and light helium nucleus plus gamma radiation plus 5.49 MeV energy is released, in which the deuterium and hydrogen combine, hydrogen that means the proton, to produce light helium nucleus and gamma radiation with release of 5.49 MeV energy. So first these three processes occur, and after that this light nuclei of helium combined with other light nuclei of helium to form again the two proton or the two hydrogen. First we repeat these three processes again. Here in sun and the star, here the two types of the cycle take place. One is the proton-proton cycle and second is the carbon-nitrogen cycle. The fuel in the sun is the hydrogen or the proton and in its core, and hydrogen burned into the helium. Okay. The proton-proton cycle is represented by the following reaction. One hydrogen combined with the other and the deuterium plus positron plus neutrino plus 0.42 MeV energy is released. Right? Again, the hydrogen or the proton is combined with the proton. Deuterium is formed plus positron plus neutrino plus 0.42 MeV energy is released. In which, in this process, two hydrogen or the proton combine to produce the deuterium plus positron neutrino with the 0.42 MeV energy released. Now, this positron combined with the electron and two gamma radiation with 1.02 MeV energy is released. In this process, the positron and electron combine to produce the two gamma radiation with 1.02 MeV energy released. Now, this deuterium combined with the another hydrogen or the proton and produce the light helium nucleus plus gamma radiation plus 5.49 MeV energy. So in which the deuterium and hydrogen, that means the proton, combine to produce the light helium and gamma radiation with release of 5.49 MeV energy. So keep in mind this reaction. Frequently this reaction asked in competitive exam, fill in the blanks. Clear it? Okay. Now after this reaction, how again the proton are produced, here we discuss it. Okay, proton cycle in the sun occurs 2 times, and as a result, the fourth reaction is that these two light helium nucleus 2He3 again combine with the another light helium nucleus and to form the helium nucleus, plus 2 hydrogen or the 2 proton plus 12.86 MeV energy is released. Again, due to the occurring of earlier 3 processes twice. So as a result, we obtain the 2 light helium nucleus. These 2 light helium nucleus combine with each other to form the helium nucleus plus 2 hydrogen or the proton plus 12.86 MeV energy, in which the 2 light nuclei of helium combine to produce the nucleus of helium and 2 proton or the hydrogen nuclei with release of 12.6 MeV energy. In this process, the 2 light helium nuclei combine to produce the nucleus of helium plus 2 proton or the 2 hydrogen plus the release of 12.86 MeV energy. For the fourth reaction, this reaction occurs only, the first reaction must be occurred twice. Due to the first reaction occurs twice, then the fourth reaction is take place, because in fourth reaction the another light helium nucleus is required. The net effect of this reaction is, first reaction occurs 2 times, second reaction occurs 2 times, third reaction occurs 2 times, and fourth reaction occurs 1 time. There is the shape of reaction will be as the 1H1 plus 2 electron plus 2 He4 plus 2 hydrogen or the proton plus 2 neutrino plus 6 gamma rays plus 26.7 MeV energy is released. During the 1 proton cycle, here the first reaction is started with the 2 proton or the 2 hydrogen nuclei. After the fourth reaction completion, we obtain the 2 hydrogen as a product. 2 hydrogen as a product, and due to that result, this cycle is known as the proton cycle. In 1 proton cycle, total 26.7 MeV energy is released. Clear? Okay. This reaction is also can be written as 4 hydrogen or the 4 proton plus 4 electron. So as a result, 1 helium nucleus plus 2 electron plus 2 neutrino plus 6 gamma radiation plus 26.7 MeV energy is released. Clear? So that is the proton cycle occurs in the sun, in the star. In short, the 4 hydrogen, that means the proton, combine to form an helium nucleus or the helium atom with release of 26.7 MeV energy. Again we repeat it. What is the fourth reaction? After the discussion of the 3 reactions. In fourth reaction, the 2 light helium nucleus combine to form the helium nucleus plus 2 hydrogen or the proton is produced plus 12.86 MeV energy is released, in which the 2 light nuclei of the helium combine to produce the nucleus of helium and 2 protons with a release of 12.86 MeV energy. For the fourth reaction occurs, the first 3 reactions must occur twice. Because in fourth reaction, the 2 like helium nucleus is required. Due to the one set of the 3 reaction, 1 like nuclei of the helium is produced. Second set of the 3 reaction, another like helium nucleus is produced. These 2 like helium nucleus combine to form the helium nucleus plus 2 proton plus 12.86 MeV energy. So this complete set of the reaction is occurs like this way. First reaction 2 times, second reaction 2 times, third reaction 2 times, and fourth reaction 1 times. There is a set of reaction of proton-proton cycle, and that can be represented as the 4 hydrogen plus 2 electron combine to form the helium nucleus plus 2 hydrogen plus 2 neutrino plus 6 gamma rays plus 26.7 MeV energy. This set of the reaction is also written as the 4 hydrogen combined with the 4 electron. As a result, the helium nucleus plus 2 electron plus 2 neutrino plus 6 gamma radiation plus 26.7 MeV energy is used. Clear? So that is the proton-proton cycle occurs in the sun, in the star, and that is the source of energy in the sun, in the star. So here the theory of this chapter is completed. After that, the illustration of this chapter, the first illustration 13.1. Given the mass of the iron nucleus as 55.85 atomic mass unit, and atomic mass number A is equal to 56. Find the nuclear density of iron. Mass of the iron is 55.85 atomic mass unit. 1 atomic mass unit is equal to 1.66 into 10 is to minus 27 kg. R0 is the constant, 1.2 into 10 is to minus 12 meter, and atomic mass number of the iron is equal to 56. Okay, here we require the density. We know the equation of the density is equal to mass per volume. Mass per volume. Mass of the iron atom is given in atomic mass unit. Here volume is required. Volume of the atom is, here we consider the atom as a sphere. Therefore the volume of the atom is V is equal to 4 by 3 pi r cube. Here the radius is not given. First we have to calculate the radius of iron atom. By using the equation R is equal to R0 is to 1/3. Therefore, radius of the nucleus iron nucleus R is equal to R0 is to 1/3. Here we substitute the value R0 is 1.2 into 10 is to minus 12. A atomic mass number 56 raised to 1/3. Now the simplification is that 1.2 into 10 is to minus 12. And 56 raised to 1/3 is 3.825. Therefore, the multiplication of these two quantities is 4.59 into 10 is to minus 15 meter. That is the radius of iron nucleus. Now, what is the volume of iron nucleus? Volume of iron nucleus is equal to 4 by 3 pi r cube is equal to 4 by 3 pi 3.14. Radius already we found, that is the 4.59 into 10 raised to minus 15. 10 raised to minus 15 raised to 3 cube. Clear? Okay. So as we simplified, we obtain the volume is 4.05 into 10 raised to minus 43 meter cube. That is the volume of iron nucleus. Now mass is given, volume we obtained, therefore the density of iron nucleus is density is equal to mass, that means the MFE upon volume. Mass of the iron nucleus is given 55.85, that is in atomic mass unit, convert into kg. Therefore 1 multiply with 1.66 into 10 raised to minus 27 kg, divided by the volume 4.05 into 10 raised to minus 43. As we simplified, so we obtain 22.89 into 10 raised to 16 kg per meter cube. That can be written as 2.29 into 10 raised to 17 kg per meter cube. So that is the density of the iron nucleus. That is the required answer. Again, very easy numerical. Given the mass of the iron nucleus is 55.85 atomic mass unit and atomic mass number is 56, find the nuclear density. Here mass is given 55.85 atomic mass unit, constant R0 1.2 into 10 raised to minus 12 meter, A is 56, atomic mass unit relate with the kg by this constant 1.66 into 10 raised to minus 27 kg. To find out the density, we know the equation of the density, mass per volume. Mass is given, we have to find out the volume. Here we consider the nucleus as a sphere, therefore the volume of the sphere is 4 by 3 pi r cube. That means we also require the radius of nucleus of iron. And therefore, first we need to calculate the radius of iron nucleus. By using the equation, R is equal to R0 raised to 1/3. When we substitute the value of R0, A, we simplify it. So we obtain the radius of iron nucleus is 4.59 into 10 raised to minus 15 meter. Now, the volume of the iron nucleus V is equal to 4 by 3 pi r cube. Here we substitute the value of radius, this 4.59 into 10 raised to minus 15. So volume of the iron nucleus is 4.05 into 10 raised to minus 43 meter cube. Now the density of iron nucleus is mass upon volume. Mass is given in atomic mass unit, convert into kg, that means we have to multiply by 1.66 into 10 raised to minus 27 kg. Divided by the volume 4.05 to 10 raised to minus 43. As a result, we obtain 22.89 into 10 raised to 16 kg per meter cube. Therefore, the density of the iron nucleus is 2.29 into 10 raised to 17 kg per meter cube. So that is the density of the iron nucleus. So this type of the numerical may be asked. Instead of the iron, the another nucleus is given. Here the atomic mass and also the atomic number are different. So we can calculate the density of the any given nucleus. Clear?